So, hello to everybody who's in. My name is John, and I'm going to be leading today's webinar talking about AP Physics. Let me see if I can find that page. There we go. All right, so today we're just going to go through the test, talk about some general strategies, review some material. Sorry, the Zoom reset, so I don't have my EP branded background on just now, but um, yeah, going to go through things. Feel free if you have any questions throughout, can either, well, actually, you have to put them in the chat. So can put them into chat, can make it to the host or panelists, or can make it to everyone. That way, I'll be able to see it and can answer them as they come in. I'm going to try my best to keep an eye on the chat as we're going. Okay. All right. Yeah, with that, I think all good to go. So let's just jump into things. So first and foremost, this is me. Been doing teaching and tutoring for upwards of 15 years now. Excuse me. Um, got bachelor's degree in chemistry from Gettysburg College, PhD in chemistry, University of Chicago, but I do know my physics. So don't hold that against me. Okay. And yeah, I've been TA in grad school, liked that, and that's how I got into teaching in general. Okay. But enough about me. You're not here to hear me or see me. So this session all about the material and also some approaches. So we're going to review the material and along the way can talk about a few things to keep in mind, like certain traps to help avoid. Just make sure I upload this so I have a copy. So yeah, we'll look through all of the different units that we have um, and look at the specific topics within them. But first, let's just do a quick discussion of the test structure. Now, I won't spend too much time on this. Might have already been prepping for this all throughout the semester if you're taking this AP course right now. So you know kind of the gist of things here. So, multiple choice section, free response section, both of those or each of those is 50% of the grade. And note that multiple choice, 40 questions, but 80 minutes. So we get 2 minutes per question, which is a good amount and good too, because sometimes, as you know, there's a lot of reading involved with questions. Okay. Oh, yeah. And then the free response, 100 minutes for four specific questions, each one of them a different type, and they appear in this order: mathematical routines, translation between representations, experimental design and analysis, and then qualitative quantitative translations. Okay. So, for these free response questions, the more intense one tends to be experimental and design and analysis. It's something kind of different compared to those other questions that are there. We got to figure out an experiment to measure something, and then they actually might give you data to then graph in a particular way to get a quantity. So if there's one to put time into, it's that one. But as we'll see, it's okay to skip around. Might be good to do that one at the end just so that you free up the other ones and then have more time maybe to work on that particular question. Okay. All right. Scoring. So on the multiple choice, I'm only going to highlight this because this lends to our strategy. It's out of the 40 questions, it counts how many you get correct. And note here that each question is worth the same amount. Okay. So they don't care about material that you put on like a scratch paper or work on a scratch paper, right or wrong. That's it. Every question's the same. But for the free response, those are graded by hand. They're looking for specific things. They are looking at what you write down. And note that there's a point distribution here. So translation between representations, 12 points, 10 points for mathematical routines, experimental design, 8 points for the qualitative quantitative transformation. So if we had to pick ones to focus on, could maybe get the easy 8 points first and then work our way up. Or like we said, experimental design can sometimes be the tricky one. So maybe the mathematical routines, get that out of the way and then come back around to the more difficult. All right, take both sections, put them together. You get a scaled score from 1 to 5. Because each is 50, so each will count for 50%. So the problems with this whole setup, at the end of the day, it is a lot of material. You got to know a lot of stuff, might not be familiar with everything or might not feel confident with everything. But we're going to try working on that today. And also, we can plan around that lack of confidence too. Okay? Second, there is math. Most students don't like it. And also, this math is on the more difficult side because there's a lot of algebra going on, maybe not exactly calculating values. Okay. So we have to know how to manipulate equations. And I don't know, sometimes just plugging in numbers and working with them is easier. So that makes it more difficult, the algebra aspect. Okay. A lot of reading going on. So we need to pick out necessary information and then put it all together. So that's why you want to make sure you give yourself time to read through things. Okay. And I mean, another issue adding on to that, there is not that much time to do everything though. So you have to pace yourself and plan accordingly to use your time as effectively as you can. Okay. So while preparing, here are just some good things to think about. So, first point here, really focus in on your strengths and also your weaknesses. What are you good at? What aren't you good at? What topics do you like? What topics don't you like? Can you handle the conceptual questions or do you like plugging in numbers? All of that together will tell you, hey, maybe I need to put more study time towards this topic. Or will tell you, hey, when I come to this question, it's a topic I'm not as confident with. Maybe it's best to just skip it, find another I'm better at, and come back to this one. Okay. So knowing strengths and weaknesses, big part of what we're going to look for, or big part of what you want to look for. Okay. The next part is a plan. We can study and study and study until we can't study no more. But if we don't have a plan going in there, things can easily fall apart. Okay. And this is where knowing the strengths and weaknesses helps out a great deal because that can tell you which questions you can skip over. Which one should I try out, which to come back to? And not just that, when you come across a question, maybe you don't want to kind of do everything right away. Think about a process of elimination plan. What should I do sitting down here that will help me work through all of this? Okay. Or what can I eliminate? You don't need to know the answer right away. Okay. Now, the third point, interesting thing, you want to make good use of that formula sheet. So you get the formulas, a lot of things are on there. They kind of explain things, but know what's there, know what's not there. That will tell you, hey, maybe I should memorize this. Or if you don't see something there, good to kind of keep that in the back of your mind. And this particular point, I always stress to students it's a great way to review concepts. All we have to do is go through the equation sheet. Okay. So go through the equations. Try to ask yourself when do I use this? What does this represent? And could even try playing around with the equations, maybe like reorganizing them, which fit with forces, which go along with conservation of energy, which could maybe be used for both. Okay. All of those equations are there, and you can use them to help yourself out. All right. And finally, I always recommend that students do this at some point. So, College Board hosts past FRQs. They typically just go back 3 years, but AP Classroom should have a few more. They also give you the rubrics for those FRQs. So, we can go into an FRQ thinking, okay, I nailed that, I got everything across, but the rubrics tell you what specifically they're looking for. So, it's good to just give that a peruse through for a question. Maybe try it out yourself. Then take a look at the rubric. See, well, okay, I'd get points for this and this and this, but I don't have that. And they also have example or sample responses too. Compare it to those. This will help you figure out, hey, what will give me the points? And also, what could I maybe avoid? Okay. Might not have to say everything. Maybe you can get through things a bit quicker and just have to show one thing, and that will get you the point. Okay. And it's a good way to look at phrasing and terminology. What do they say when looking at the question? Or what material or theorem do they mention? Okay. All right. So come down, sit for the test. And again, all of these are kind of bleeding together because they all work together. General strategies at the end of the day, show them what you know. Okay. Work the easier questions first. That's true for multiple choice or FRQ. Skip the tricky ones, come back to them later. I always get students who think, oh no, I should start with the harder ones, use up that time, then I can go to the easier ones. that could work out, but an issue there is if there are questions towards the end that you know how to do and they would have been easy points, you might miss out on those if you don't have the time after working the harder ones. So, really try to focus. Don't spend too much time on one question. My rule of thumb here, because you have the 2 minutes, if it's approximately 30 seconds and you're not sure what to do, best to just skip it and move on. Okay? Yeah, I've had students who they're sitting down, they work on something, then realize minutes have passed and they still have a bunch of the tests left. So don't let that be you. Plan out which ones to do first based on the topic. And oh, that reminds me, when I use the word easier here, that means easier for you. Everyone is different. I can't sit here and say, oh, yeah, it's always going to be these that work out. So, yeah, prioritize it around you. What do you feel best about? What do you think is easy to get through? Next, read the questions carefully. A lot of information in them. Highlight anything that may affect your approach. So, one common one, like at rest. If you see that, that tells you something about the speed at that point. Highlight it, information. Or if we're looking at collisions, if it says that it's an elastic collision, highlight that. That tells you something about it, will affect kind of how you approach the problem. Okay. So, yeah, look out for those phrases. Use that highlighting tool to help find things. Typically, you don't have to highlight variables. Those are always going to be easy to find in the sentence, and then you just read around. So, it's really those phrases or the words. That's where they can hide things. And then it's always good to identify what topic the question's testing you on, even if you can just narrow it down to a particular unit. The reason why is because once you know the unit, then you have an idea of, oh, hey, formula sheet, I know these apply to it. This gives me a place to start. So, yeah, when it comes down, if you can narrow down the topic, like, oh, I know that this is about energy and even gives you a jumping off point. Well, all right, what energy do I have? Is it kinetic? Do I have potential? Do I have both? How do I relate them? It gets the ball rolling for particular questions. So, yeah, when I say topic, that could be like a unit or like a specific concept, whichever works. All right. Few more things, I promise. Then we'll look at some physics. So, multiple choice. Kind of broke this into a separate slide, and we're going to get some examples with this. All of the problems I have today are multiple choice problems. Sadly, free response, hard to fit on particular slides. Okay. But working through it, same kind of idea with the general strategies from before. Okay, and we might get to talk a little bit about those at the end. Or if you have any questions, can throw them in the chat and I can answer them at the end. Okay. So process of elimination is going to be key for these. Don't need to know everything right away. Eliminate answers where you can. Sometimes that involves breaking up the answers into parts. Sometimes the parts are easy to identify, other times not necessarily. Like if you have to look at whether things are increasing or decreasing, and let's use energy again. Oh, what's happening with the kinetic energy? What's happening with the gravitational potential energy? And then it lists out different options. If you feel more comfortable evaluating gravitational potential energy, can do that first. Start with that, eliminate the answers that don't match what you have, and then can look at kinetic energy. Okay. Really divide and conquer here is the big thing. Okay. Think of ways, well, hey, this isn't the case, that isn't the case. Yeah. Third, look out for keywords in the answer choices. So this can help again with where to start or what to eliminate. If you're told that, oh, the velocities are the same because of conservation of momentum. All right, conservation of momentum gives you a place to start looking. Or maybe, hey, let's analyze it using that. And then can start from there and go on. Or you can look out for things that don't make sense. This is true because the force is directed downward. Well, no, if it's not directed downward, can get rid of it, move on. So yeah, watch out for the wordings. This is helpful for wordy answer choices. And then evaluating general trends first. Don't have to know again the answer exactly. Should I get something larger? Should I get something smaller? Maybe compared to another value, maybe like looking at numbers. Okay. Also, maybe it just need to know what variables the answers might have. Oh, well, okay, force of gravity is responsible for this torque. Okay, so the torque expression should have mass and acceleration due to gravity in it. Any answers that don't, get rid of it. Okay, so starting with the general, all of those really tie in with the divide and conquer. Okay. Looking for little ways to kind of move yourself closer to the goalpost and get rid of the things that are nonsense. So, all right, now before getting in, let's look at a concepts breakdown. The reason I bring this up is because it helps with that first general strategy, strengths, weaknesses, and what to focus on. So, note here that the big sections, force, translational dynamics, and work power and energy, 18% to 23%. If you want to put in more effort studying, if you don't feel as comfortable with those, these are the ones that are good to review. Hey, even if you are comfortable, still good to review. Make sure you're feeling comfortable. If close to test time, Unit 6 and 7, energy and momentum of rotating systems, oscillations, these are ones that are good to maybe hold off on. Maybe like a few days before can look at these because the real points and the weight comes from those other sections. So for these, oops, now let me use orange again and save to review. All right, so put the energy where you need to, focus on maybe the greens and the others. Orange ones, can help out. And the good news is for oscillations, there's really not that much material in there. Energy, momentum, rotating systems, a little more. But we'll see that now. So let's begin with some material review. I can go through these as fast or slow as all of you want to. Again, if there are any questions, feel free to throw them into the webinar chat. Can just make it like to the host, and that should be private to me, or you can make it everyone could see it. Okay. And I can always address it. I'll keep an eye on it. Yeah, let's start with some kinematics. So describing motion, going back to the beginning, we got displacement, velocity, and acceleration. And note that velocity, acceleration are looking at the changes in other quantities. Okay. Change with time specifically. So velocity looks at time. Oops. I might do that a lot during this review. Let's use my pen instead of my highlighter. Okay. Yeah. How do the positions change? That can tell you something's moved. Velocity, how fast it moves. Acceleration, how fast the velocity is changing. And yeah, the good thing to note here too, all of these are vectors. I didn't add the arrows above for these, but keep in mind, if I don't have the arrow, it's just going to be a magnitude. Uh, and then direction, I can always like explain or I'll show where the direction is in like a figure. But for instance, if I have a ball that starts there, the displacement, let's say it moves over to the right. So then my displacement is here. And we can set up our directions however we want. If it's in a line, typically plus or minus. So I can say, what? There's my axis. Let's say that's X, and this is positive. Okay. So that's a positive displacement. And then if I look over here, this is a negative displacement. Okay. And then to get there, we'll if it goes there in a specific time, it will have some kind of velocity. Pointed to the right, it's in that direction. Pointed to the left, in the opposite direction. And then if the velocity changes, there's some acceleration. So yeah, be on the lookout, pluses or minuses. For these quantities, they mean something. And a problem will typically tell you what the direction should be because they don't want you to kind of switch things around on it. Okay. So yeah, oh, and I'll add here too. So the direction can be plus or minus in a line. All right, so looking at some graphs. So if I need to show what's happening, graphs are a great way to do it. Okay. Few different things happening here. So no velocity, displacement graph is staying flat because it's just in one place. Velocity is 0, acceleration is 0. Constant velocity, I see my displacement changing, changes by a straight line. Velocity stays flat and acceleration flat at 0. So it's not changing. Therefore, the velocity isn't changing, so acceleration is stuck at 0. Same for both of those two things. Okay? And quick note here. So the slopes of these charts, good to know how they're related to different quantities. The slope of the displacement tells me what's happening to the velocity. Okay, positive change going on here, that's why the velocity is positive. Okay. And then if I look at the velocity, slope of velocity tells me about acceleration. Well, that slope is 0, so the acceleration is at 0. Okay. So yeah. So in general, the slope in the graph gives us a rate of change. So the slope, actually I'll say slope of graph gives rate of change. Now that rate of change might not always mean something, but for these, slope of displacement versus time is velocity. The slope of the velocity versus time is acceleration. So they might ask you to actually pull that from a graph. Here's the displacement. What will the velocity graph look like? I'll just have to look at how it's changing. Yeah, constant acceleration, displacement swoops upward because the velocity is changing. So I get a bunch of different slopes here. So velocity is changing and it's increasing. Gets steeper, larger velocity. Yeah, and then the velocity has a slope to it now. So there is now an acceleration that's positive. Okay. So this shows something speeding up. That's when the velocity and acceleration have the same direction. So note that it depends on direction. It could be moving in the opposite direction and still be speeding up, in which case velocity and acceleration are still are both pointed to the left. Okay. So note same direction. So that's if velocity is that way and acceleration is that way. Or maybe it's the opposite. Yeah, constant deceleration, all the opposite. Here, the displacement is kind of curving down and the slopes are getting steeper. So the velocity is getting smaller and the velocity is sloping down. That's why the acceleration is negative. Okay. So in this case, yeah, do the same color. So this is the opposite direction when decelerating. So velocity that way, I would then have acceleration going the opposite way or vice versa. There we go. There are graphs showing what they're doing. The other thing to note, area underneath things, the area under acceleration curve gives the change in velocity. So that will tell me, hey, positive area, so the velocity increased over that time interval. Whereas here, it's negative because the 0 is that top line. So the change in velocity, it decreased overall between those points. And then velocity, the area under that, good to know, is the displacement, change in position. Yeah, it's telling me the change. If I know where it started, I would add that change to the displacement. So initial position plus displacement, the net change tells me the final position. So just have to keep an eye out for that too. Okay. And note in both of these cases, moving to the right, so the displacement is positive, but slowing down in this last one. So even though this is sloped downward, the area underneath is positive, so we did see an overall change, an increase in the position. But then eventually it will start going back the other way, right? Kinematic equations. These are kind of hit or miss for students. If there's one thing to remember here, it's that they are for when acceleration is constant. Okay? The acceleration changes, I can't use them. So good to know just kind of the ins and outs. They're there. I believe all of these are on the equation sheet, so you'll have access to them, and they might be a little different. The displacement, that can also be written as xf minus x naught. So you might see this equation, xf equals x naught plus v naught t plus 1/2 a t squared. It all in all means the same thing. Initial position minus final position, that's our displacement. Okay. I can apply these in each dimension. So if I wanted to, I could look at, say, that first equation for y. I mean, it really doesn't matter how I organize these, as long as I keep them straight in my head. VF, so final velocity in the y direction, initial velocity in the y, plus acceleration in the yt. Yeah, or I could write that for the x coordinate. Either way, they will still work as long as I can break it up into the components. So one use of this is projectile motion. So the trajectory is always going to be parabolic, and I'll use this to illustrate kind of breaking things up. Might be already familiar with this from a while ago, good to review. So our initial velocity, vector pointed in that direction, if I know the angle here, so theta, I can break this up into two components. The initial velocity in the x direction, sorry, let me clean that up a little, and then let me raise that arrow a little. An initial velocity in the y direction. So two different components. To figure out the magnitude, just have to use trigonometry. And again, pay attention to that equation sheet. The trig relationships are on the equation sheet. Okay? So can use that too to help kind of review. But if I need to know here, the initial in the x is going to be the initial times cosine theta. And then for the y, that component is the initial times sine of theta. Can go back to SOHCAHTOA. Opposite, adjacent, can turn that into a triangle. There. And there's the angle. So that's our vector, that's a vector, that's a vector. So that's v naught x, v naught y, and then just v naught. All right, good point to know on this. So we always have gravitational acceleration, or acceleration due to gravity, acting downward. Because that's not happening in the x direction, the x velocity doesn't change over the course of this. So because of that ax, I could essentially just rewrite this as Vx, because that's not going to change, but it's the V naught in the y direction that will be changing. Okay. Good point to know. At the top here of the trajectory, so that is when the ball's motion in the y direction has completely stopped and it's going to go back the other way. So there is only the x component of the velocity at that point. And then it will go back down. If it starts at that pot spot, ends at that same kind of height or spot, it's going to have the exact same velocity when it gets down to this spot. So it was, I think, like that, but now pointed down. So that same magnitude as the initial velocity, but now going downward. If it fell off a cliff, that weren't true because it's going to spend some more time accelerating. That arc, that point is the halfway between these two. So it spent the same time decelerating going up as it will accelerating going down. So the speed becomes the same. And yeah, acceleration due to gravity. So I can plug this into any of those equations and then rewrite them for projectile motion. So the big one, delta y is what? V naught yt minus 1/2 g and then t squared. Minus sign because it's always accelerating downward. And feel free to make the calculations easier. 9.8, I can always say that that's about 10 meters per second squared. All right. When faced with a problem here, I'll also add this. The time spent in the air is always dependent upon the y dimension. So you'll use that to figure out how long it's up there. And then the x coordinate you would use to maybe just figure out how far to the side it goes or the range that it goes to. So yeah, times with the y component, x is just along for the ride. All right. Quick talk about relative motion. Motion is always described relative to some reference frame. So in this first picture, there's an observer on the shore here watching a boat on the river. So they see the speed of the boat, but the speed of the river also contributes to that. Okay. So they're actually seeing the boat go by with the river speed also incorporated into that. Okay. If I move the observer to in the water, maybe they're like in an inner tube floating next to the boat, they're seeing a different speed for that boat because they are now in the river. They're moving with the river. down this. So in order to convert from that reference frame into another, all we typically have to do is add or subtract vectors. So yeah, so the equation that we have here, if I want VA observed by B, I would get V observed from the ground and subtract the speed of B observed from the ground from that. So it's all vector addition. Did it down here, flip the speed of the boat or the river, then I get the speed of the boat relative to the river. So the observer will see it moving slower. Same thing if you're in the car on the freeway, you're going one way, you see another car going the other way. It looks like it's going very, very fast. Okay? If you think of yourself as the observer, you kind of flip your speed around, add it to that other one. So that's a much larger vector going that way. So yeah, relative motion going to be all about adding or subtracting vectors at the end of the day. I'm not sure how much that appears. I typically don't see that much of this type of question. So this is one can like put on the back burner for now. All right. Let's try out a question or two. And I put in more questions than we might have time for. So just so that we had things to look at. We can always come back to certain ones if there's time. So this particular question, what have we got? A small cart rolling freely on an inclined ramp with a constant acceleration. Okay, so constant acceleration, that's a phrase that I can highlight of 0.50 meters per second squared in the negative x direction. At time t equals 0, the cart has a velocity of 2.0 meters per second in the plus x direction. So I get another direction. I'm highlighting those because they're not incorporated into that number. If the cart never leaves the ramp, which of the following statements correctly describes the motion of the cart at a time t greater than 5 seconds? The reason why I would raise my eyebrow at that, these were all given at t equals 0, but now we're looking at some time further down the road. So things could potentially change here. All right. So using our strategies, divide and conquer, is there anything that I can do here? Well, note that in these questions, they're talking about direction of travel. So that's part of the answer. Plus x, minus x. Then they also talk about speeding up and slowing down. So I can evaluate those in whichever way I want to. I could start by looking at the x direction. I could start at looking at speeding up or slowing down. The key thing for those, remember, is what direction the acceleration is in and the velocity vector at that particular time. But let's look at that 5 seconds. So at 5 seconds, let's see what's actually happening here. So if I use my kinematic equations, I know acceleration, I know the initial velocity. Let's just look at what the velocity is at 5 seconds. So the equation that I can use, VF equals V naught plus AT. And then I can just plug things into here. So VF is equal to, so let's start with the velocity. That was 2.0 positive x, so 2.0 meters per second. Acceleration was 0.50, but in the negative x direction. So actually, that's negative 0.50 meters per second squared. And then my time, 5 seconds. All right. Might be able to see where the math is going. Sometimes we don't have to finish off the math. But if I look at this, I'll get my 2.0, and then I'm subtracting 2.5 meters per second. So that gets me a velocity negative 0.5 meters per second. So at 5 seconds, it's switched direction. So now it's changed direction. So in that case, if the acceleration is negative, it's just going to keep moving it in that same direction. So right off the bat, now I can eliminate things. Now it's moving in the negative x direction, so I can get rid of A and B. And then in terms of speeding up, slowing down, I can say that it's going to be speeding up because the acceleration is in the same direction. So there we go. Putting those pieces together, breaking it down one by one, start with a calculation, might not need to go all the way. If you note that, oh, well, that's going to give me a number bigger than 2, but I'm subtracting, I can say it's in that direction. I was going to switch direction. All right. So looking good for that one. So had to note they tried to trap us here 5 seconds. We're not looking at it where it is initially. So I got to figure out maybe just the speed. The position displacement isn't going to help me out here. All right. Let's try out another one. Yeah, let's do this one. So this was part of a multiple part, but I only put the one that was related to this material. So a small block of that mass goes down the track, shape of a circular arc, after it's released from that height, and it leaves the track on this side at an angle of 30 degrees at a speed of 3.0 meters per second. And it's some height above that. So looking at my question, after the block leaves the track, what is the block's speed when it reaches the highest point of its motion? Well, after it leaves the track, what type of motion does it have? Well, it's a projectile, so it is going to go in an arc. And the highest point of that motion is right up top here. So now what was the special thing that we said about that point? Well, the speed in the y direction, or the velocity in the y direction is 0. It only has the component of the speed in the x direction at that point. So if I find that speed at the start, then I can figure out the answer to this problem. So I want to know what the magnitude of that component is. And the equation that we mentioned before, use cosine. So 3.0 meters per second times the cosine of 30 degrees. And now it gives you values for this on the equation sheet. If you happen to remember from like calculus or pre-calc, you know that it's some like weird number, √3/2. But think about it. If I look at my answers, I can get rid of 0. It's not the x component that's 0, it's the y component that's 0. So they're trying to trick us there. I know it's not going to be 1.5, that's exactly half. 3.0 is too big. So whatever this value must be, I mean, I could plug it into my calculator and check it. It's likely going to be 2.6. So try to avoid the math when you can. See if there, like we said, any trends or anything that we can look through that will help us eliminate answers. All right. Let's end with one more practice problem, just because we mentioned it before. And this is a good check of eliminate answers in a matter that is easy to do. So what have we got? We got a velocity versus time graph. And we want to know which of the following statements is true about it. I'm going to bet that some of these might be easier to evaluate than others. So if you come across one that seems difficult, you can maybe move on, see if we can eliminate another. So, case in point, A, talking about how it is not moving from t equals 4 to t equals 10. Well, let's see, where is that portion in the graph? It's right here. Well, okay, that is just a constant speed, but a constant speed is still moving. So constant speed, okay, but still moving. So that answer, no, out the door. Trying to set up a trap, if this were displacement, that would be true, but velocity, not true. Okay, B, objects' initial and final positions are the same. Oof. That one, I don't even want to kind of check because that one involves, like we said, displacement, and displacement is the area under the curve. So I would have to like evaluate all of this to figure it out. That seems like the trickier answer to evaluate. Hmm. So what I'm going to do, I'm just going to skip over that one. Maybe there's other ones that I can eliminate that are easier. So case in point, let's see C, what's going on? The object is slowing down from t equals 14 to t equals 16. So where is that? Right here. So slowing down means um, acceleration is in the opposite direction. But because we have negative values and they get more negative, the speed is actually increasing here. Beforehand, when it was a positive speed, so before 14 seconds, then it was slowing down. But after that, then it's going in the other direction, but the speed increases. So that's not true. Oops, let me cross things out. Not slowing down. It wasn't not moving. And then how about D here. So it's asking about the average acceleration and how it's different between these two regions. So if I look at those two regions, that right here and right here, average acceleration, kind of a calculation because I have to look at the slope. So I have to do a calculation, but I think on the easier side than having to figure out the area of trapezoids or break it up into multiple triangles. So here, if I look at how it's changing, it's a change of 10 over 4 seconds. Okay. So that is 5 halves. Here, it is a change of 5. It increases by 5, and that's over 2 seconds. Oh, so no, those are actually the same acceleration. That's not true. Can eliminate that one. So B is my answer here. I didn't need to check that. They're hoping that you'll try checking it and then waste all the time checking that one. So then you might not have time for other questions. Okay. So if something feels long or it might be difficult, skip over it, even if it's a whole question. Come back to it later. All right. Looking good for that. Let's talk about some forces. Okay. So, center of mass, mentioned this. It's a weighted average of all the masses in the system. It's like a balancing point. We can say that it's almost as if all of the mass is located at this point here. So yeah, these are different ways to calculate it. Note that it's typically closer to the more massive points. Okay. So two masses over here, that's why it's closer to those two. And right in the center here, because they're all evenly distributed. And then a little closer here, but there are more mass on that side. So kind of in between those two areas. Yeah, I can always think of systems like a point there. Let's talk about Newton's laws. Forces are pushes or pulls, but specifically an external force changes an object's velocity. And it could do one of two things: change speed or change direction. Or it could do both, actually. So, three things. So, for instance, look at this picture on the left, moving to the right now with some velocity, but then it stops. So, that tells me that between those 2 points, there must be a force, and that force is directed, or the net force is directed to the left. All right, change the speed of it, slowed it down. In this case, we changed the speed and direction. So if I had to take a guess here, let me draw another ball. So maybe at this point, it has to experience a force to go in that direction. Maybe the force just entirely in the y direction. So it gets some net force or external force, pushes it upward, that causes it to move in that direction. So yeah, if something changes direction or changes speed, likely going to be a force that's responsible for it. So the second law, well, we can say that acceleration, because it's a change in velocity, has to be related to the net force on the system. So that gives us an equation that looks like this, that sigma just means to sum up all of the forces that act on it, the system, and then it's related to the mass times that acceleration. Okay. Now, on your equation sheet, they wrote it a little differently, but it's all the same thing. Actually, they didn't put F net. I believe they used the sum notation. So they're trying to make it look complicated. All this is saying is add up the forces, divide by mass. That tells you your acceleration. So could see that both ways. The other point, forces come in equal but opposite pairs. That's our third law. Okay. These specifically refer to contact forces. And let's take a closer look at that. So side note here. These pairs are when forces are in contact. Each one exerts a force that acts on the other. And the trick here is just to kind of flip the wording of the force. So if we have force of A on B, to get the action reaction pair, we just look at the force of B on A. So if the object that's in there changes, then they're not action reaction pairs. So in this case, if I look at the book, the force pointing upward is the force that the table exerts on the book. So the action reaction force should be the force of the book on the table. So be very careful here. especially when it comes to normal forces. The gravitational force is not an action reaction pair with a normal force. Okay, those are second law pairs. They cancel each other out because the object is not moving. So they are the same because they have to be. But if I were to push on that book, the normal force increases. That's because the force that the book exerts on the table is now larger. It's both the gravitational force and the force that I apply. So for gravity, remember, it's the force of the Earth on the object or mass. Sorry, let me try to clear that up a little bit. Okay. So force Earth on the object. So the action-reaction pair is the force that the object exerts on the Earth. So those would not have the same. In this case, I guess I can say book. So it's not action reaction pairs with that because I can't flip it. One has table, one has earth in it. All right, looking good. So forces, push or pulls, said that. Bunch of different types of forces. Typically, we will draw free body diagrams to represent magnitude and which direction they act in. Now let's just do a quick look at all these different forces. So gravitational force occurs between things with mass, always acts like the shortest distance between them. So on the line between. So sun and earth here, got a gravitational force going that way and another one going that way. And they should have the exact same magnitude, but opposite directions. All right. Another good point about this one, close to the Earth's surface, we can rewrite this as just mg. And that's because the big G, big M, so the mass of the Earth in this case, radius of the Earth, they're approximately constant along that surface. So they're not really changing. Even if they do, it's by such a small amount that it doesn't really change the force of gravity. Okay? So we'll use this equation typically when looking at objects that are like in space, and this equation just when we're looking at things at our level, close to Earth. Okay? And the other thing to note here, so this acceleration due to gravity actually comes from those terms. So little g is equal to the gravitational constant and then the mass of Earth or the mass of whatever planet we're looking at, and then the radius of the planet. All right. Earth is about 10. We can always manipulate this if it's another planet. Normal force acts as a contact force. Okay. So that was the one that was responsible, the force that the book, a table exerted on the book. And it is always perpendicular to the surface. Now, one thing to note, mentioned it a little bit before, the normal force represents an apparent weight. So if you use like a scale, the scale is actually measuring the normal force. So that's why if you pushed on someone on a scale, the value that it reads would increase. Okay? So we only feel weight because we feel the ground pushing back up against us. Okay? That affects how we feel in roller coasters, maybe on elevators as well. Yeah, so normal force, interesting facts about that. Tension always just carries a force between two objects along a string. So in these cases, the two tensions that we're looking at have the same magnitude. Okay. Moves things along the string until we get to another object. So it's always along the direction of the string, cable, or chain as well. Friction, a little more interesting, occurs when two surfaces try to move past each other. So it's a sliding motion. They're trying to resist that sliding motion. Okay. Static friction when they don't move. Kinetic friction occurs when they do move. Okay. So the thing to take away here, so kinetic friction, that equation is just the kinetic friction that you get. But static friction, note this little less than or equal to. So this value on the right side represents the maximum static friction force that you can get. We might not actually reach that. Friction, the static friction will always respond to whatever force you apply. So like in this case, if I apply a force of 5 newtons, the block doesn't move, kinetic or the static friction force also has to be 5 newtons. If I increase it, force is 6 newtons, static friction force would be 6 newtons. I can keep increasing it until I reach that maximum. After that, that's when I go into kinetic friction. And note, These two coefficients are not going to be the same. Okay, typically, coefficient of kinetic friction is less than that of static friction because once you get something moving, it keeps moving. First law. Yeah, so that it will always be some kind of response to an applied force. Okay. So actually, if you plot applied force and friction force, it would be well, actually just a horizontal line. Yeah, because it will always try, well, no, a vertical or slanted line until it reaches the maximum, then it becomes kinetic. So just watch out for that. If it's less than the maximum, then the force that's applied is the friction force. All right, spring forces. Springs don't like it when you push on them or try to pull them. So the force that they exert will always be in opposition to whatever displacement you try. Okay? And here, K is just the spring constant for that. Tells you how kind of sturdy, not sturdy, how rigid it is, how much it wants to kind of get pulled out or in. Yeah, the key thing here to note though, it's always in response to some kind of displacement. At the equilibrium, no force exerted. When you start moving it, that's when the force is exerted. And note direction. Opposite direction as how it's displaced, opposite direction as how it's displaced in the bottom one, too. There we go. Final thing to look at here, uniform circular motion. A specific kind of application of forces, I'll say. So for this, it's the uniform circular motion in general. It's when an object moves around a circle at a constant speed. Now the speed is constant, but the velocity is changing, as the picture denotes. These purple arrows are what the speed or the velocity vector is. So it's changing directions all around. Now, to describe it, we can use the period, how long it takes to complete one rotation and come back, or frequency, which is the number of rotations completed in a second. And there is a way to then relate those two together, period and frequency. Okay? If the period is the time to complete one rotation, frequency is the number of rotations per second. 1 over the frequency would give you a time, that time is the period. Yeah, and then we also get this relation down here that's good to note. So the speed of the object around this depends on both the radius and also the period. Mm, That makes sense. That top quantity, 2 pi r, that's the circumference of a circle. So it goes around that distance in that time, divide those two, you get speed. And then we can also relate it to frequency by just replacing the 1 over t, where, yeah, here, actually, I can write this out too. The inverse of this is also true. Frequency is also 1 over the period. So, yeah, so how is the force acting on this? Well, a centripetal force is a force directed towards the center. It keeps the object moving in that circle. And these are the two equations that represent it. So the acceleration, v squared over r. And then with like force equals ma, if we want the centripetal force, we just multiply by m as well, whatever the mass is. Okay. So think of this as like you moving around the circle and just getting a tap, tapping it back into the circle at each point as you move around. So that direction should always be towards the center. It's there to kind of keep it in. So yeah, here, same thing. I drew in those force vectors. All right, so here's a key example of a force can change the direction of velocity without changing speed. And because of the speed, that force has to be tangential to it. All right. Centripetal force, though, just a label. So it's not like a specific force. It could be just a label that we apply to some force that is directed toward the center, that keeps it in that motion. So maybe it could be one force, like in this case, satellite orbiting Earth, the force of gravity is what keeps that satellite in that motion. Maybe it could be the sum of forces. So, like swinging this bucket, sometimes it will, both cases actually, I add the tension and also the weight together, and that difference is the centripetal force. It's the net force directed upward at the bottom here. At the top, though, I add together the weight and the tension. So add them up there. That gives me the net force directed inward. Usually there'd also be a tension force if, like, I'm really swinging it fast. So to keep it in the circle, I have to have a large centripetal force. Or it could be a component. Car banking on an incline, there is going to be a component of the normal force that's exerted that's directed toward the center of the circle. And actually, that's why banking helps out. It kind of reduces what the car has to do, specifically the friction in the wheels needed to keep a car moving in a circle. But all together, what do these things tell us? Or what's true? They're always directed toward the center of the circle. So, all right, let's just do a few practice problems, maybe one or two, so we can keep moving. So, for this one, elevator is traveling upward, but we're told that it's slowing down. So, highlighting useful information, slowing down means the acceleration is directed in the opposite direction of the velocity. Then we have relationships here. FA, magnitude of the force exerted on box A by box B. And then FB, magnitude of the force exerted on box B by box A. And then we're looking at a gravitational force, specifically the one on box B. So I could add that in. So like right here, I'll say that it's directed. Yeah, downward. And then we want to rank the forces. So if anyone's ear was ringing while reading that, or hearing me read it, I guess, magnitude of the force that box A exerted on box A by box B. So that would be like B exerts on A or B on A. So that would be like that direction. Then it was the force exerted on B by A. So A on B. Well, hey, I can just flip those label around. These are action reaction pairs or third law pairs. That means that they have the exact same magnitude. So divide and conquer, once I find that fact out, let's get rid of things. Well, no, that's not true. A and B should be equal. And no, they're not one less than the other. So C and D are out. And now I have these two options. Now we could probably eliminate it just on the basis that it's accelerating downward. But if I think about it, here, let me sketch on FA on B first. In order for the acceleration to be pointed downward, Newton's second law, the net force has to be downward. So comparing the gravitational force and that force that A exerts on B, that means that the force due to gravity has to have a larger magnitude because that's the one pointed down. So if I isolate B, the force of gravity is going downward. Sorry, that should be red. And then that other force directed upwards. So the net force is pointed down, which is exactly what we want. So that's B. So therefore, F of G has to be greater than both of those. So our final answer for this one is going to be B. End of the day, forces act in the same direction as acceleration. So if I know that, I know where the force is going. Okay. Yeah, we can skip over that one. Same thing here. So here we get two graphs of Vx, Vy. And then we want to figure out the force diagram that shows the forces exerted on each object that agrees with this. So if I'm looking at it, remember, forces, same direction as acceleration. Well, I have velocities, so I need to compare this to acceleration. Well, in the x direction, what? This is flat. So because of that, my slope is equal to 0. So that is my acceleration in the x direction. So there is no net force in the x direction. And I can immediately go through, divide and conquer, eliminate answers based on that. So if I look at these, okay, A checks out, ooh, but not B, because if I break it into components, there is going to be a net force there. So that's out. Let's see. C would be okay, because I get that direction, that cancels out that one. And then in this direction, yeah, it cancels out. It's okay. A is out. Now I got to look at these other ones. It's all right. For the next plot, EY, well, that sloping downwards. So the slope is less than 0, which means that the acceleration in the y direction is less than 0. So there should be a net force downward in the y direction. Now let's eliminate some more. A is out because those cancel each other. So now between C, let's see, I move that over. That is my Y component. Oh, nope, those also cancel up and down. So C is out. So my final answer has to be D. And just to check, look at the Y component. There it is, the bigger arrow pointing down than up. So there will be a net force in the negative Y. And there we go. Ooh, and I'll write in here too. So these cancel, so they're okay. Yeah, so this is a good example of a question that can incorporate multiple topics into it. Need to think about the slope and how v is changing to get acceleration, which is the thing that's actually related to the force. Yeah, so looking good there. And I think with that, let's keep going. Let's make sure we talk about a few things here. So energy, potential to do work. So that can be used to change an object's motion. Kinetic energy, that formula typically doesn't give students much trouble. Mass and velocity, I just need to know those two things. Potential can be a little different. Usually it's energy stored because of a conservative force. And the thing that can make it tricky is setting the zero for it. So we can pick where to say that our potential is zero. And we'll look at instances for both types that we have. Gravitational potential. So the general equation, so this is the one that I could use for like objects in space again. It goes along with Newton's law of gravitation. And note that this negative sign makes things a little bit tricky. So that negative sign means um, larger values are actually smaller. And then as I get further away, the potential energy is increasing. So as R increases, so as R increases, as I get further away, potential energy also increases. And the zero that we typically set for this at R is infinity, so the objects are separated as far as they can, the potential energy is zero. They no longer like feel the gravitational force at that point, so there's no potential energy to talk about. Close to the surface, typically we set our zero as the ground and then compare everything to the ground, but we don't have to. If I'm at the top of the cliff, I could set the top of the cliff as the zero, but then I'm going to have some negative potential energy because I can also go below the cliff. So setting zero might change how we do problems, but if you set it at the ground, that gives you a good point. Can always start there. Maybe look out for ways to make it more interesting by changing the zero. All right, spring potential. The zero here is set at the equilibrium position. Spring hasn't been compressed or extended, so there's no energy that it's holding on to or storing. And then note that it doesn't matter which side we go to, compressing or extending, the potential energy is positive. In the end, it's trying to pull it back, but the amount of energy doesn't matter if I move it one direction for 1 meter or the other direction 1 meter. Yep. So 1/2 k delta x squared. Yep. So work, change in energy due to a force acting over a distance. Yep. So the key thing here is that the force, we typically care only about the parallel component to the displacement. So if force is already in the same direction as the displacement, like here on the left, just multiply those two together. If the force is directed at an angle, but the block moves just in the x direction, I don't really care about that force going upward. I only care about the component that is changing the motion of it. So I would only be interested in this component, so the parallel to the displacement. And then that's where this cosine theta comes from. So if I look at that angle, I'm looking at the part at the bottom, so the adjacent side to the angle. So the parallel is the force times cosine theta. All right. Thing about work, it can change kinetic energy, which makes sense. Like we said, force changes motion, it can speed things up. So in this case, it's making the block move faster. And to figure out how much faster, we can use that work that we calculate and relate it to the kinetic energy. So change in kinetic energy is equal to the net work done by external forces. And a good point to be careful of here. Note that if I apply the same force over the same distance to an object, the change in kinetic energy has to be the same. That is what this theorem is telling us. but where they can get you, and this is why I have to read carefully, may not be the same change in speed. So the v value might be different for the two. And the reason why, it depends on the mass. Okay. So pay close attention to the wording. Same amount of work, same change in kinetic energy, that doesn't necessarily mean it's the same speed. The more massive object is actually going to be moving slower. All right. Looking at graphs, another thing to look at, like the kinetics or the other quantities at the beginning, the motion. When I graph the parallel force versus distance or displacement, the area under the curve is equal to the work done on or by the system. So from our work kinetic energy theorem, this is also then the change in kinetic energy. So a question that could give you that graph, ask the change in kinetic energy, or maybe even change the speed to switch it up. Then you would look at the area underneath it. Total mechanical energy, add up all the different types of energy. If there are no external forces that act on an object, that has to be conserved. Energy needs to go somewhere. So typically what we can do, say delta E is equal to 0, or really just take a snapshot at the beginning and at the end, calculate the energies for those and compare them. So quick example that shows up here, escape velocity. I'm not going to go through the whole thing in essence of time. The final picture here, the kinetic energy and potential energy are 0, so that's where it just escapes. Okay. The initial given by those values, so when I set it up, those two have to equal 0, and when I go through and solve it, escape velocity, square root of 2 big G m over r. So if any object getting close to a planet or maybe close to Earth has that escape velocity or even a little above it, it's not going to get pulled in by the gravitational force. It's not going to go to orbit it or get stuck by that force. All right. And one quick note here, defining the system. They like to throw in things, questions about systems where they might mention one object but not another. One case in point here, including Earth in the system. When they include Earth, then a gravitational force is an internal force. Technically, we are looking at both objects that exert the force, so it's a force that's within that system. Energy is going to be conserved. It's not really doing work on it. But, I mean, if I don't include Earth, I still get the same things because the force due to gravity is an external force, so it is doing some amount of work on it. So basically, be careful. If Earth isn't included, then we don't have to worry about potential energy and gravity as an external force. Or we don't care about gravitational potential energy and gravity is an external force. Okay? So yeah, technically, conservation energy only applies to the system on the right. So just have to look out for that. And then power, rate at which energy changes over time. Only thing that I'll mention here, because change in energy, work is a type of change in energy, I can rewrite those two equations. I think you might be given both of them on the equation sheet. And then down here, the instantaneous, we'll note that that force, parallel force again, actually, let me use a different color. It is the force times cosine theta. Okay. It's just like we did when we were looking at work and the force was directed at an angle. Okay. Average is over a particular time. Instantaneous is right at a given instant. All I need is the force at that time and velocity. Well, speed in this case, no vectors to calculate that. All right. Yeah, maybe just one. Let's do this one. This will highlight a strategy. So block is held at rest against a compressed spring at point A, and at rest. Good to mark that. At the top of a frictionless track of height h is shown above. Block is released, loses contact with the spring at point B. So maybe that will help. Contact with the spring at point B and slides along the track until it passes point C, also at height h. How do the potential energy U of the block Earth system and the kinetic energy K of the block at point C compare with those at point A? So this is a great divide and conquer strategy. I could look at either kinetic energy first, or I could look at the potential energy. of the block Earth system first. Now, because for potential energy, close to a surface, that's dependent on height, mgh. Because these are at the exact same height, has to be the exact same potential energy. So this depends on height, same energy. Immediately get rid of C and D. Now I just have to consider the kinetic energy of the block. So one thing to note, they gave us a spoiler here. It was at rest at A. So the speed was 0, meaning the kinetic energy was equal to 0. But at C, well, over on the left, when it was at B, it will have some speed. So there is some kinetic energy that will then carry through over to point C as well. So they can't be equal to each other. C is going to be bigger than Ka. Yeah, and conservation of energy. Potential energy is the same. The spring had energy initially, but there was no spring after. That had to go in the kinetic energy at C. So if anything, I could even avoid B because conservation of energy holds. All right, good quick look at that. This problem's a trap. The masses of the runners are different. The length of rope is different. But thinking of it conservation of energy, because they have the exact same speed, they will actually go to the same maximum height. So our answer to this one is B. And that's B. I got B because we're told in the problem that he swings to a maximum height of 1.8 above the ground. So why doesn't mass matter? Well, if I look at kinetic energy before 1/2 mv squared, and then they'll have some kind of potential energy after. I'm not great at drawing stick figures. There we go. And that will depend on mgh. But note in this case, the m's cancel. So really, 1/2 v squared equals gh. So h only depends on the speed. I don't have to worry about mass. I don't have to worry about length. Those didn't factor in. And note that the height would be defined like relative to the ground. So the height is not the length of string or rope that's there. All right, let's keep going. So linear momentum, vector quantity, just velocity times the mass of the object. You can say that momentum is like a quantity that keeps an object in motion. And one thing to note, more massive objects will typically have more momentum, especially when the velocity is the same. So this picture below, if I'm driving, if both the car and the truck here are traveling at the same velocity, the truck has more momentum because it's more massive. So that means that, like, if it gets rolling, it's going to be harder to stop that than it would be the car. Okay? So you want to get out of the way when the trucks come in. With the car, still get out of the way. But that's why they designed whole roads or sections along roads for runaway trucks to drive up. Okay. All right, momentum can change if velocity changes, or technically if mass changes. Change in momentum, final minus initial. And change in motion occurs due to a force. So forces cause a change in momentum, and actually they're related to the rate of change of momentum, as shown in this equation down below. So that equation you're actually given, F net is equal to delta P over delta T. So if I want to know the change in momentum, I can take the net force and multiply by the time that it's applied over. Very similar to what we saw with work, but now we're looking at time. And this was just like a quick derivation of why that is. It all follows from Newton's second law. You'll get copies of these notes after, so can take a look at this afterward. Yeah, since that force and time seems to be important, it gets its own name. It's known as an impulse. So like kind of like work, except again, looking at a time, not looking at different distance or displacement. Okay. So, because we said before that force and time, or change in time, is a change in momentum, impulse momentum theorem tells us that I can relate those two. So, in the end, this is kind of what we wrote out before. The impulse or the change in momentum is an average force over time, or times a time interval that it's applied. All right. So when looking at graph relationships for these, if you graph momentum versus time, the slope is equal to the net external force. So that comes from that relationship that we talked about before. F net is delta P over delta T. The area under the curve is equal of a net force time curve, sorry, is the impulse exerted on the system. So based on what we saw in the previous slide, this is also going to be a change in momentum. So if you see that graph thrown up at once change in momentum, looking for the area underneath it. But just pay attention to the axes here and what's plotted on them. All right. Center of mass, basically this is to say that center of mass, I can also think of that as moving, so it will have its own velocity. So when the objects in it are moving, I can think of it as a point particle that will have some velocity in that direction. Okay. And this equation here, so it's really just the equation for the center of mass, but we replaced, or position of the center of mass, but replaced the x with v. Well, this quantity, m times v, is momentum. So it turns out that the momentum of these particles is what's related to the speed of the center of mass. Specifically, the total momentum is related to that. And why that matters is because of conservation of momentum. No external forces are exerted on a system. The velocity of the center of mass is constant, it doesn't change. The total momentum is conserved as well. Okay. Kind of play around with each other. But yeah, similar thing here. I can look at the initial state of the system and the final state, add up all the quantities, and then put them together. Note that we can break this into x and y dimensions. Um, Most problems don't look at you calculating that. They typically care about like one component, maybe. Could have you look at vectors, but again, vector addition, just have to make sure that whatever the momentum vector, total momentum vector looks like beforehand, that's what it looks like after, even if they're all kind of moving around in different directions. But yeah, conserved, good to just break it up, initial and final, and think of those separately. So this particularly helps with collisions. In collisions, when objects collide, and here's a point to remember, they exert forces on each other, specifically ones that are equal and opposite. That's an easy trap. They say it collides, but like a more massive particle exerts a bigger force. That's not the case. Contact force between them, it's the same magnitude on both of them, but opposite directions. Well, because they're the same force, over the same time interval. Together, these 2 points tell us that the impulses that they exert are equal and opposite. Okay. So is anything really changing here? No, both of them are going to transfer the same amount of momentum to each other. And it's an internal force, doesn't change the momentum of the system. So inelastic and elastic collisions. Momentum, note the thing at the bottom, is always conserved in these. We can always use that to evaluate collisions or different interactions. Energy, however, does not have to be conserved. Okay. In elastic collisions, it is conserved. So think of like a ball bouncing perfectly, kicking a ball, or this Newton's cradle over here. Clean transfer, I can calculate the kinetic energy of the ball at the end and the ball at the beginning, and they would be the same. In elastic collisions, energy is going to be lost. Typically, objects might stick together. That's going to be a perfectly inelastic. And in that case, the energies before and after are not equal. Okay? So what happens is that force that we have, it's non-conservative and goes into doing some kind of work on that system. Typically, it deforms something, like in the case of the collision, the car crash or car accident. It does damage to the car, that takes away energy. That's why they're not the same before and after. So yeah, noting these words in a question can help out. It tells you what other things you can use. So in general, like if I have multiple objects, two objects colliding, I can use conservation of momentum, but I need to know pretty much all the other velocities except the one that I'm calculating. But if it's elastic, conservation of mass is, or conservation of energy is fair game. I can now use two equations. That means that I can have two unknowns in it. Although it's computationally crazy, it's possible. Perfectly inelastic, because they stick together, the final speed is going to be the same for both objects. We can think of it as one thing, and then it just has some total mass. Oops, there we go. So m total. So there's one less velocity that I need to consider, one less speed to consider, and if it's perfectly inelastic. Okay. But yeah, knowing those words help you figure out what you can consider. All right. And I think maybe just one here too. Let's do my favorite. Where are you? There you are. So two astronauts connected by a taut cable and are initially at rest. Good thing to highlight. With respect to a nearby space station, astronaut X throws a large container to astronaut Y. Figure 1 above shows the astronauts immediately after the container is thrown by astronaut X. Figure 2 shows the astronauts immediately after the container is caught by astronaut Y. Which of the following describes the motion of astronaut Y in these figures? Okay. So, conservation of momentum going on here. Because the two were at rest initially, their speeds, I guess I'll call it Vx naught, Vy naught, are equal to 0. So initially, there is no momentum. So then what does that mean for us? Well, divide and conquer, I can take a look at both figures separately, or I can take a look at each figure separately. First one, we were told this object was thrown over there. So now it has some speed. I don't know, let's say what did they say? It was a container. Yeah. Let's say VC initial or VC. If momentum is conserved, there was no momentum before. So the astronaut, specifically astronaut X, has to move over to the left to balance out that momentum that the container has. Well, because they're combined or they're pulled together by the tight string there, cable, that is going to pull astronaut Y over to the left as well. So in this case, after that's thrown, astronaut Y moves to the left, so I can get rid of does not move, and now I'm down to B and D. Well, now in the final picture, if they caught it, that container is now at rest. So that means that the astronauts' conservation of momentum also have to be at rest again. So final here, y final, that equals 0. So once again, they're at rest. They do not move. My answer for this one then is D. Okay. They like throwing out these types of problems. Oh, you're in space and you throw something. Because the object leaves with a speed, you also have to have a speed going in the opposite direction. Now, it won't be the same speed because mass plays a factor here. So we can always then do conservation of momentum to figure out what the speed should be. But yeah, it will be like frictionless surface. Throw something, what does that do to the momentum? All right, let's look at some other topics. I can go through this one quickly. Rotational quantities, very similar to their linear quantities. In fact, a lot of the equations that we have here are just the linear ones, but with different variables in them. So that can save you some memorizing from the equation sheet. Just note that if it's rotational, I just swap out variables in those equations. So, case in point, angular displacement, angular velocity, angular acceleration, very similar to the equations that we had before. Okay. Angular velocity, change in angular displacement over time, acceleration, change in the angular velocity over time. Now, when we're looking at these, they also have direction. Typically, the direction, though, will depend on clockwise, counterclockwise, and we can still say that it's positive or negative. Once again, like for a problem to be very clear, it might tell you which direction to consider positive and negative. But for your purposes, for a problem, you can pick whatever. It shouldn't change the answer. Yeah, but direction-wise. So if this is like a whole disk and I focus on some point on that disk, the angular displacement is the angle that gets swept out in a particular amount of time. So like right here, that would be my my angular displacement. Okay, all right. Moving from that point to that point, there was then some angular velocity. And both of those quantities would be positive. If they went in the other direction, I would make them negative. Or if I just flip the signs, I just flip all the signs for them. Okay. The key thing here, direction. So in writing pictures, good to show that direction. Okay. Kinematic equations describe motion now when angular acceleration is constant. Okay. These all look exactly the same as the linear ones. Displacement now is angular, the velocities are angular, the acceleration's angular, but nothing has changed. Okay. For our purposes, typically you're always rotating in a plane. That's why I didn't put anything about breaking it up into the x and y dimensions. There really isn't like a y dimension here. We just have to think about like positive, negative, clockwise, counterclockwise around the axis of rotation. All right. We can still relate that motion to one another. Okay. So if I go through some kind of angular displacement and trace out where the particle travels, because it's some radius away, it moves along this path right here. Okay. So it does go through some kind of distance as it goes through that angular displacement. And it turns out that that distance is just the arc length of whatever circle it's going to be moving through. Okay. Well, to get that, I take my angular displacement and multiply it by r. And I do that for all the other quantities. So when I need to convert from angular to linear, I can just multiply by r. Now, because of this, for a rigid system, different points can have the exact same angular quantities, velocity, acceleration, and displacement, but they can have different linear quantities because that depends on r. So in these two examples, closer to that axis of rotation, smaller r value, so a smaller distance that it goes through. Okay. Further out, it goes a larger distance. So that means that it has to be traveling faster the farther it is away. So the farther away it is, okay, from that axis of rotation. And then that picture on the far right, that's like looking at a disk again at certain points. Not all of the points on the disk have the same linear speed or linear displacement moving through that circle. All right, still have to describe forces. Well, that's where torque comes in. Torque is essentially just a rotational force. We'll find that we can rewrite the laws of motion for rotation. Torque is responsible for changing rotational motion. So in these cases, I look at the lever arm, which is the distance from where I'm rotating to where the force is applied. And then I only care about the perpendicular component of the force. Okay. The perpendicular component is what's going to cause the rotation. Okay. So if I were to look at this force acting on the wrench, I really just want that perpendicular component to it. And here we see another use of trig. So the perpendicular force is just F times the sine of theta, where theta is the angle between that lever arm and the direction that the force is going in. Okay. So note here, unlike the forces that we had before, this one depends on kind of like where it's applied. So if I apply a torque, and let's make it on this picture. If I apply a torque halfway perpendicular, it's going to be a smaller torque. Okay. It could even be the same magnitude, but because it's halfway through, I get essentially half the torque I had before. And if I apply the force along the moment arm, so parallel, doesn't do anything. Why? Because again, torques are responsible for rotation, and that force doesn't cause any rotation. I can push on the edge of a door all I want. It's not going to make the door rotate. I have to push it kind of in the direction that I want it to go. And note too here, it doesn't make sense for me to try to push the wrench right by the head because that's going to be such a small torque, not going to be effective rotation. Typically, I want to apply it as far away as I can, and that means I'm going to be using a smaller force to do it. So small forces can produce big torques if I apply them far away from the axis of rotation. So force is a little different. Inertia is different too, no longer just mass, but moment of inertia or rotational inertia. Okay. Formula for this is just an object mr squared. So again, something that depends on the distance from the axis of rotation. Okay. If it's a collection of objects, I just add up the moments of inertia for each of those objects. Now, if it's like a big thing like a disk or cylinder, the problem will tell you if it's important, or sometimes if it's not important, what the rotational inertia for that object will be. Okay. So don't have to memorize ones, just this formula is the important one. And good to note, things that are closer to the axis of rotation are easier to rotate compared to things that are farther away from it. And then one thing here, we can skip over this part. Typically, if the axis of rotation is the same or goes through the center of mass, that minimizes the rotation. Because remember, the center of mass is like a balancing point. So all of the objects are as close as they can be to that center of mass. But if I move the axis of rotation, then I get a rotational inertia that's going to be larger, and I can relate it to that using the parallel axis theorem. I am pretty sure that this is on the equation sheet. Okay. But yeah, how I use it, when I change the axis of rotation away from the center of mass, I can use this to figure out what the new moment of inertia is. All right, Newton's laws of motions. A lot of the same stuff. Instead of forces changing velocities, torques change an object's angular velocity. So, if something is not rotating and then it is rotating, that means that I must have applied some kind of torque. So maybe like a force here at the end and pointed upward because that gets it rotating in the right direction. So there's a torque, starts rotating. Kid on a seesaw, exert a force downward due to gravity. Nothing there to cancel it out on the other side, so this will cause the seesaw to tilt to one side or causes a rotational, an angular velocity. Well, what do we do if we want to know angular acceleration? Well, angular acceleration is related to the net torque on the system. Now forces are torques. Angular acceleration is related to torques, just like acceleration, linear acceleration related to net forces. Add them up, and then other change, instead of mass, it is the moment of inertia of the system. A lot of the same stuff, different variables. Rotational equilibrium, the torques cancel out. So if I add another kid to that side of the seesaw, I'll have what? Torque is equal to maybe some positive value here. Here it's equal to some negative value. Those two, if I add them together, would cancel out. They're trying to cause different rotations. Now, if one of them moves a little closer, different torque, then they might not be balanced anymore. So the key thing is balancing out torques. That will depend on the distance and also the forces exerted. And the trick here, the velocity does not change. So either the system remains at rest or it continues to rotate, but the velocity is constant. Okay. It's the same for linear motion. Net forces might cancel out, but if the object has a velocity, that just means the velocity is not changing. So it could move with a constant velocity, or it just doesn't move at all. So watch out for that phrasing. Having a velocity doesn't mean that there has to be a net torque. You can have a constant velocity, but no torques or no forces are acting on it. Sorry, I should have said forces. Oh, and separate from translational equilibrium, if I put wheels on this seesaw and then I just gave them a push, it would continue not to rotate. It would be in rotational equilibrium, but it could be traveling with some center of mass velocity. All right. And I think, just to be safe, let's talk about a few more things. And you'll all be getting a copy of these notes. A lot more to look at here, so feel free to peruse it and help out. Ooh, this is a good example of knowing the forces to look out for. Torque is what? The lever arm times the force. The mass acts at the center, so I'm looking for L/2 as my lever arm. So that means I can get rid of C and D right away. So it goes to show, hey, think about what variables we expect, can break it into parts and check those. So because the last two typically not as bad, let's finish up with just a few quick things about rotations. So there's also rotational kinetic energy, rotational inertia times the angular speed squared, much like the one for linear. Again, still falls similar equations, different variables that we put in. Hmm. Yeah, if a lot of things rotate together, we can add up the kinetic energies. If it's a rigid system, I can look at the total moment of inertia and just use that to evaluate it. Work and torque? Hey, forces did work, changed kinetic energy. Torques can do work over an angular displacement, and they change rotational kinetic energy. And same idea as before. So watch out for this trap. I can exert the same torque over the same angular displacement. And that means that it has to have the same change in kinetic rotational energy, but not necessarily the same change in angular speed. And why is that? Because that will then depend on the rotational inertia, or I, of the system. All right. Angular momentum keeps things spinning. Can say it keeps the world turning, which is actually true. Momentum, mass times velocity. Here, moment of inertia, rotational inertia times angular speed. Okay. And the thing to note, I can relate this to linear momentum. So in this top, if I look at a point, I can figure out the momentum of that point, and then I just have to multiply that by r, and if there's an angle between them, sine of that angle. I think on the equation sheet, you get the RMV sine theta. I put in the momentum just to show that the relationship is between linear momentum. Oh, and then total angular momentum is the sum of all those points. So that would just be for that point. If I wanted the whole thing, I'd have to look at each individual point, which can be a pain. You won't have to do that. Same thing, change in angular momentum. If the angular speed changes, the angular momentum changes. That will be due to some torque acting over an interval, and we can kind of rapid fire through these. There is some angular impulse, that is the torque times the change in time, or the time that it's applied, and that angular impulse is equal to the change in angular momentum. Okay. And oh, same graphs from before for momentum apply here as well. Force over, or torque over time, area underneath is the same as the impulse, it's the same as the change in angular momentum. And then we can conserve angular momentum. A good thing to note for this, kind of different from before, changing the mass distribution, so changing the rotational inertia, also changes angular speed. So the big thing, figure skaters, arms are spread out, they have more mass further away. Remember, it's harder to rotate that. So they will have a slower angular speed than if they bring their arms in close to the body, close to the axis of rotation, they'll spin faster. Okay? So the distribution of the mass is going to play a role, specifically looking at rotational inertia. All right. And with a few minutes left, I'm just going to talk about one more thing, rolling without slipping, and specifically the point on the next slide. If an object does move, the center of mass moves, it can have both translational energy and rotational energy. Now, when rolling without slipping, it's usually a static friction force that causes the rotation. So that's applied at the point of contact. Okay. And in this case, there should technically be another force that's applied like at the center to cancel that out. But if you're looking for the force responsible, it's going to be friction. That causes the rotation. So that torque is what we would be interested in if we wanted to look at the rotation of it. Okay. So when it's rolling without slipping, I can apply these same relationships that we did before and relate everything to the motion of the center of mass. Okay. So if I know the center of mass velocity, I can figure out what the angular velocity has to be when it's rolling without slipping. Okay. Same with the acceleration of the center of mass and angular acceleration. But the thing that I want to point out, so we have to incorporate this then into our energy calculations. So there will be an energy term. Note that this can mean that objects that roll have a slower speed for their center of mass. Mm. So in this case, I have a block that will slide. We can say that the plane is frictionless, and a ball that will roll down there. If they start at the same height, they have the same gravitational potential energy. But then at the bottom, the block will move faster because it only has translational energy, whereas the ball will have both translational and rotational. So the energy from the potential energy gets put into both of those, meaning the center of mass isn't going to move as fast as the block does because some of that energy is making it rotate too. Okay. So that's the thing to watch out for. It's a good way to eliminate answers, saying, oh, okay, here it will have rotation at the end. Well, that rotation, that potential from before goes into rotational and translational. So I can then compare it to a situation where there isn't rotational. All right. I think with that, we're at time. Got through a good chunk. Hope that working the problems helped out, discussing the strategies. Feel free, there is a lot more information in here. Should be getting sent copies of this and can look over the notes that I have put together for this. Can be a nice little study guide to help figure out what do I need to review, what do I need to go back and look at, and also have some of those um the side notes that I've been calling them. Things to consider that will help out with applying it to problems. So with that, hope you enjoyed. If there are any last minute questions, can feel free to put them in the chat. I'll stick around for just a little bit. Um, if there are any questions, I'm happy to answer any little after time, but if you'd like to get going, I understand. So thanks again and good luck on the test. Remember, play to your strengths. Probably one of the biggest things.